Hello dear friends, welcome my channels. Today's discussions is hydrogen atom quantum mechanics. So friends, before the hydrogen atoms, we will discuss the Bohr model of the atoms because this is very important for this is the fundamental. So I need to discuss. So the basic postulates of Bohr theories are the atom consists of a small heavy positively charged nucleus in the center, surrounded by electrons. The electrons in an atom revolve around the nucleus and only in certain selected circular paths which have a fixed value of radius and energy. This path is called orbit. So friends, this path is called orbit. I have already drawn. This is called nucleus, this portion, and electron is moving. There is electron moving around the nucleus, and this path is called orbit. I hope I can clear this concept. Yeah, I think this concept is clear for everyone. This path is called orbit. The energy of an electron in the orbit does not change with time. In other words, as long as the electron remains in a particular orbit, it does not lose or gain energy. This means that the energy of the electron in a particular energy shell remains constant. Therefore, these orbits are also called stationary states or allowed energy states. The term stationary does not mean that electron is stationary, but it means that the energy of electron does not change with time. This accounts for the stability of an atom. Only those orbits are permitted in which the angular momentum of the electron is a whole number multiple of h divided by 2 pi, where h is Planck's constant. The energy is emitted or absorbed only when the electrons jump from one energy level to another energy level. This is the energy emitted one energy level to another energy level. So friends, this is the Bohr postulates, which is very fundamental but important to discuss for hydrogen atom. Now I want to introduce hydrogen atom in another one of our atom, hydrogen atom. Hydrogen is the simplest of all elements with a single proton. Hydrogen with a single proton and a single electron However, its importance cannot be overstated. Hydrogen is by far the most abundant element in the universe, making up 74% of all baryonic matter. For example, the sun is mostly made of hydrogen in the context of quantum mechanics. The hydrogen atom also plays a really prominent role because it is one of a very select group of quantum systems that we can actually solve analytically. As such, the hydrogen atom is used as the starting point to understand more complex quantum system. For example, other atoms we have. In this video, we are going to introduce the hydrogen atom, and we are also going to set up Hamiltonian. Hydrogen atom is the simplest of all atoms. It is made of a single proton and single electron. So let's start with a proton. In SI units, it has MP. MP equals to 1.67 times 10 to the minus 27 kilogram. The proton has electric charge Qp and its value, the element charge that we typically denote with the letter Qp, equals to E equals to 1.6 into 10 to the power minus 19 C means coulomb. Let's now consider the electron. It has mass ME equals to 9.11 times 10 to the minus 31 kg. The electron has electric charge equals to QE, which is equal to negative elementary charge in SI unit. It is equals to minus QE is equal to 1.6 into 10 to the power minus 19 coulomb equals to E. So what do these numbers mean? Let's start with the masses. The ratio of masses MP over ME is given by this number equals to 1.833. In other words, the proton is almost 2000 times heavier than the electron. Let's explore in more details the large mass difference between the proton and the electron. For the hydrogen atom, it's actually not such a big deal because we can actually solve the eigenvalue equations of the Hamiltonian analytically. The mass difference between proton and electron still proves convenient because it helps us gain some conceptual understanding. Electron in field of proton atom is helium, lithium, etc. So Ma divided by Me greater than Mp divided by Me. In particular, we are going to see later in this video that the large mass difference between proton and electron means that we can almost think of the hydrogen atom as an electron moving in the electrostatic field generated by a stationary proton, but this is only really beginning of the story. Remember that hydrogen is the lightest of all elements, which means that for any other element starting with helium, lithium and so on, then the ratio of the mass of the nucleus to the mass of an electron will be even larger crucial. Unlike hydrogen, we cannot analytically solve the eigenvalue equation of the Hamiltonian of other elements. The same is true for multi-atom systems such as chemical compounds on material. There are no known analytical solution to the corresponding Hamiltonian eigenvalue equations in all of these cases, requiring the mass difference between atomic nuclei and electrons become hugely important because it allows us to separate the motion of the heavy atomic nuclei from that of the light electrons using the so-called Born-Oppenheimer approximation. This step hugely simplifies the equation of quantum mechanics in multi-atom system and forms the basis of most numerical solution to the corresponding Hamiltonian eigenvalue equation. In a way, we could say that much of our quantum mechanical understanding of chemistry, material science, and condensed matter physics relies on the large difference in the masses of atomic nuclei and electrons. But for now, let's go back to hydrogen. So friends, in hydrogen atom, according to the Bohr postulations, this is the proton, this is proton, this is proton, and this is electron, one electron. So this is one electron, and this is called orbit. This orbit is called, this orbit is L shell, L shell. This is the, and this is plus, and electron is minus, negative, and distance, if we say this is r is distance between proton and electron. Let's start. Proton is proton in hydrogen atom. Proton MP is equal to 1.67 into 10 to the power minus 27 kg, and charge of the proton is 1.6 into 10 to the power minus 19 coulomb, and electron ME 9.11 into 10 to the power minus 31 kg, and QE is equal to minus E is equal to minus 1.6 into 10 to the power minus 19 coulomb. Let's now turn to the charges. We see that the proton and the electron have opposite charges of equal magnitude. Let's first assume that the proton and electron are classical point particles. Let's also draw a coordinate system 2 dimensions, but it is trivial to generalize this to the 3 dimensions. Let the proton be at this position Rp and let electron be at this other position in two charge classical point particles interact and electrostatic potential. V Rp Re equals to 1 by 4 pi epsilon 0 Qp QE divided by mod of Rp minus Re, where epsilon 0 is vacuum permeability. So in here V Rp and Re equals to minus 1 by 4 pi epsilon 0 square divided by Rp minus Re mod of Rp minus Re. Now, using the values of the charges in terms of the elementary operation, elementary charge, we get this new expression. This minus sign here indicates that the electrostatic potential between the proton and electron is attractive. In other words, the electrostatic potential is what binds a proton and an electron to form a hydrogen atom. If we now consider the proton and electron to be quantum particles, then all we have to do is to apply the usual quantization rule and promote the classical electrostatic potential to be an operation. This means that V depends on the position operators for the proton and the electron and is equal to the same expression as above, but now the position coordinate becomes operators. We write down Hamiltonian of the hydrogen atom. Hamiltonian of the hydrogen atom. Hamiltonian H is given by the kinetic of the proton plus kinetic energy of the electron, which also takes its usual form plus the potential energy described by the electrostatic interaction 1 by plus potential energy equal to 1 by 4 pi epsilon 0 square divided by Rp minus Re. It allows us to learn a great deal about hydrogen atom. This Hamiltonian equation a great to learn deal about hydrogen neglecting relativistic terms arising from Einstein's special theory of relativity. However, modern spectroscopy techniques do allow us to measure relativistic terms, fine structure and hyperfine structure. Let R, E and P is the momentum of the proton and the positions, and Rp comma and Re and Pe is the momentum of electron comma position. For quantities, the center of mass position and the total momentum described by capital R and capital P relative position, and momentum described by lowercase p and for the center. So capital R equals to mp rp plus me re divided by mp plus me. P is equal to small p equal to small pp plus pe and R is equal to Re. So small r equals to me pe minus mp pe MEPP, sorry, position of the proton, mass of the electron, mass of the proton into position of the electron, divided by mass of the proton plus mass of the electron. Then Hamiltonian equals to p square divided by 2 capital M plus small p square divided by 2 mu minus 1 by 4 pi epsilon 0 square divided by small r cap r. This is the distance, friends. In the case, you will see atomic distance, this distance I mentioned in here. So in here capital M is equal to mass of the proton plus mass of the electron, and small mu equals to mass of the proton into mass of the electron divided by mass of the proton, mass of the electron, and 1 by mu equals to 1 by mp, mass of the proton, plus 1 by me, mass of the electron. So capital H Hamiltonian is equal to E square divided by 2m plus small p cap whole square divided by 2 mu, this is the capital P whole square, minus 1 by 4 pi epsilon 0 squared capital R cap. Now this portion is called center of mass. Center of mass Hamiltonian. This portion this is a small p is called relative Hamiltonian. So Hamiltonian for the hydrogen atom, we see that the first term only center of mass coordinate, so we can call center of mass Hamiltonian, and two term depends on the relative coordinates, so we can call them relative Hamiltonian. Let's first consider the center of mass Hamiltonian. HCm equals to capital P square divided by 2 capital M. It looks like the Hamiltonian of a single particle of total mass capital M. Therefore, we can think of it as describing the motion of fictitious particle and whose mass is the total mass of the system. Furthermore, as the only term is kinetic energy term, this Hamiltonian describes the motion of a free particles. This is the center. And now we deal the relative H relative Hamiltonian is equal to small p cap square divided by divided by 2 mu minus minus 1 by 4 pi epsilon 0 square divided by mod of R. So it looks like the Hamiltonian of a single particle of mass mu moving in an electrostatic potential centered at the origin of coordinates. Again, we can also think of it as describing the motion of fictitious particles, this time of mass mu moving in an electrostatic potential. So what does all of this mean? The center of mass of hydrogen atom behaves like a free particle. So without loss of generality, we can simply assume that the center of mass is stationary and just forget about it. The interesting physics of the hydrogen atom are therefore captured by the relative motion of the proton electron as described by this Hamiltonian. And this will be our main focus in the study of hydrogen atom. So overall, what have we accomplished? Hydrogen is a two-particle system. However, by a smart choice of coordinate, we have shown how we can reduce the problem to the study of the relative motion of the two particles, and this relative motion is described by the Hamiltonian here that looks like the Hamiltonian of a single particle. Mathematically, this is a much easier problem to solve, and Hamiltonian for the relative motion of the particle of the proton and electron will help us solve the mathematics associated with the hydrogen atom. Indeed, this is now whatever we see capital R equals to position of the proton and position of the proton plus position of the electron into position of the divided by MP plus ME. So friends, you see that MP is greater and greater than ME. So MP plus ME equivalent to MP, and it can be written this way: RP plus ME divided by MP R. Let's consider the reduced mass of the system. One by mu equals to 1 by MP plus 1 by ME. Now 1 by MP greater than 1 by m e. So 1 by mu divided by 1 by m e, that equivalent mu that implies mu equivalent to me. A good approximation think about hydrogen as simply having a stationary proton and only consider the motion of the electron. Now this analogy would in fact be exact if the proton mass was infinite, as in that case the proton would indeed be stationary. In fact, when we move from hydrogen to the heavier isotopes deuterium, tritium, they are hydrogen isotope. This is precisely what happens. Treating the nucleus as stationary becomes an increasing good approximation. Overall, this is a helpful way to conceptually think about the problem, but we know that it is technically not quite correct, because although the proton mass is much larger than that of the electron, it is not quite infinitely larger. The hydrogen atom is a key quantum system in all physics, chemistry, and material science. Hydrogen is a two-particle system made of a proton and electron. Today, we can map this two-body problem onto two simpler one-body problem, one describing the motion of the center of mass of the hydrogen atom and another one describing the relative motion between the proton and electron. Thanks for watching.